Okay, let's talk about problem number 6 now. What we have in this question is that the instantaneous rate of some value in investment, particularly, is proportional to its own value. So we're given that the rate of change of investment P with respect to time is just going to be some R, that's a number, times P. Okay? Now, given this differential equation, there's a very specific equation that satisfies this behavior. Okay, that equation is for continuous compounding. Okay, so let me just talk about that for a second. If you have a continuous compounding equation, let me just use a different color pen for now. So when you talk about continuous compounding, if you see the value or the actual principal value after t years is given by the P0, which is the initial investment in the principal, the initial principal value that you invested, times exponential to the rate times t, where the rate is the actual interest rate you get in decimal values, not in percentage, but in decimal values. So given that equation, let's take a second and try to see the derivative of it. Okay, so if you try to take a derivative of this function, what you get? You get dp over dt. So now, because p0 is a constant, it's going to stay there. Okay, and then derivative of exponential to the rt will just be exponential to the rt times r. The reason the r is being multiplied is because of chain rule. Okay, so now if you look closely, this piece in the derivative is nothing but the function p itself, because if you notice, that was just the function itself. So what we can conclude is that dp over dt is just nothing but r times p, only for a continuous compounding case. So now, knowing this fact, you know this equation right here that we got in this problem is asking us about the actual function, which is the continuous compounding function. Now what they have done here is they've given you the values. Let's talk about those. So they said if r is 2 and p of 0, which means the initial investment is $1,000. Okay, so we literally have two pieces in this equation. We know this, or we know the r. Okay, and now they want you to figure out the function p of t. It is just going to be like Lego. All you got to do is make it look like this. So p of t will just be whatever the initial value was. This value comes right here, so it's 1,000 e to the power of rate. So r is 2, so you got to use literally as 2t here. Okay, because the reason is why we're not converting this time into the decimals, because in this case they've explicitly stated the rate as r equals to 2, and if you see the equation that we derived here, that r is just literally what belongs to the power of the exponent. Okay, so that's why we're not going to translate anything. In this case, that is the only answer for this. Okay, now let's quickly jump on to problem 7. The problem 7 here in this case is using the mean value theorem. So now we're going to start talking about the mean value theorem. In this case, they've given us a function. The function in my case is going to be 10 ln x minus 3. Okay, on the interval that they gave us is 1 to 12. Okay, and they want us to actually find all the values of a number c that are guaranteed by the mean value theorem. Okay, so first of all, we need to be able to make sure that the mean value theorem is applied. It's applicable in this. So we're going to state the law first. The mean value theorem tells you, I'm going to write it as MVT. The mean value tells you if you have a function's derivative at c, some number, which represents the slope of the tangent line, that must be equals to slope of the secant line. So that must be equals to f of b minus f of a divided by b minus a. In this case, our a value is that, and our b value is that. So if you compute the value of f of b, you get f of 12. When you plug it into the main function, you get 12 ln of x, hold on, my bad, it should be 10 ln of 12 minus 3. Similarly for f of a, when you compute it, you get plug in f of 1. What do you get? You get 10 times ln of 1, and ln of 1 is 0. So what you effectively end up with is 0, and then minus 3. Okay, awesome. So once we start to figure those out, let's try to compose this piece here. Okay, so what we're aiming is we want the derivative to have this form that I just put on right here. So if there was a derivative, it should look like this. So we're going to put 10 ln of 12 minus 3, that's your f of b, minus the f of a that was just minus 3, divided by b minus a, so 12 minus 1, and that will end up in giving you a quantity of 10 ln of 12 divided by 11. In this case, there's 3, and that 3 will cancel away. Okay, so if their mean value theorem is being satisfied in this domain, there must be a point C where the derivative is going to be equals to what we just solved for. Okay, so now in order to solve for the C, let's figure out f prime of x. When you see f prime of x, you're going to get is just 10 over x minus 3. Oh, minus 0 actually. That's going to go away. Yes. Okay, so 10 over x is what the derivative is going to be. If you look at that closely, what you can do here is, add that x value, the derivative is 10 over x. So add the c value, just to apply the theorem. We're going to be very technical. That should be 10c. So now, if this thing satisfies the mean value theorem, the derivative at that value must be equals to the slope of the secant line. The slope of the secant line is this. The derivative is that. So let's equate them and solve for c. When you do so, you get 10c, 10 over c equals to 10 times ln of 12 divided by, I think it was 11. Yeah. So from this, when you solve it, you can cancel these two out, and you can isolate for c. That comes out to be 11 over ln of 12. So now this value should kind of lie in the domain, so this is the only value you're going to submit for the answer for this one. Okay, now we're going to jump to problem 8 because it's a similar approach here as well. Now the function that they gave us in f of x is going to be x squared minus 25 divided by x squared minus 16 on the interval 0 to 8. So given the information, we have to still figure out the values of c such that the mean value theorem will guarantee that. Okay, so we're still looking for the same agenda. We want our derivative at the point c to be equals to the slope of the secant line minus f of a over b minus a. Okay, so we're going to do the same stuff. We're going to figure out f of b first. In this case, the b value is 8 and the a value is 0. Okay, so let's figure this out. When you plug in f of 8, what we get is going to be 64 minus 25 over 64 minus 16. We'll evaluate that in a bit. We don't have to actually solve for it, but let's just hold on there. Similarly, when you plug in f of a, you get f of 0, which is technically just negative 25 or negative 16. So now, if you were to compose the slope of the secant line from this, what you get is 64 minus 25 over 64 minus 16 minus of minus 25 minus 16, everything divided by 8 minus 0. So this is the slope of the secant line. Let's try to get somewhere closer with this answer so we kind of have a concrete way to look at it. So let me just pull up a number. So 64 minus 25 is going to give me 39. So I'm going to get 39, and over 64 minus 16 is going to be 48. So that's those numbers. The negative 25 and negative 16, both the negatives cancel each other out, so you still end up with this. Hold on, that should be 16 over 8. So now this could be simplified a little bit more, just because I want to eventually get to that answer. Symbolically, I'll do so. So because if you want to take the LCM of these two guys, then you can see if you multiply 16 by 3, you get 48. So we can turn this into 39 over 48 minus 75 over 48, everything divided by 8. Okay, which could be further simplified to, so 39 minus 75 is getting us negative 36, and everything divided by 48 times 8. And then that's going to be, let me just check, 48 times 8 is going to be 384. So we're looking for that value. Okay, that's supposed to be the slope of the secant line. So if mean value theorem is applicable to this function in the domain of 0 to 8, we should be able to find a point C where the derivative is going to be equal to that number. So derivative time is here. So to figure out the derivative of x, first of all, that's going to be using quotient rule. So I'm going to start to do that. This thing, then you're going to keep that as it is. Derivative is 2x minus, you're going to keep the x squared plus 25 as it is, actually minus 25, my bad, times 2x again for the derivative. If you kind of simplify it a little bit, you get 2x cubed, you get negative 32x, and then minus 2x cubed again, and you get a positive of 50x all over minus 16 squared. Okay, so you see that that one cancels out. So negative 32, negative 50, or plus 50 would give you 18x. So let's go to the next page. So we got 18x on the top. We have x squared minus 16 whole squared at the bottom. This is the value of the derivative of x. So now, if we're figuring out the point C where the derivative must be equal to the secant line according to mean value theorem, so we're going to figure out f prime of c is literally just replacing the x with c. C squared minus 16 squared. This must be equals to the secant line slope that we found out. So if you equate it over there, let's see, negative 36 over 384. So let's negative 36 over 384. Now this is the point of realization right here. Okay, so when you're trying to find that value, let's try to see if you can actually solve for those. It's going to get very ugly, but we're just going to take it. So if you cross multiply and solve for c from this equation, you get 18 times 384 c, right? That must be equals to negative 36 times c squared negative 16 whole squared. Now there's a little clever catch I want to mention here. Most of the people should be able to figure it out, but hear me out for a second. Okay, we know if you're looking at this equation right here, if you're observing this equation, the right side of this equation is negative, right? It's a negative number. On the left side, on the denominator, let me just change the color pen so you can actually see what I'm trying to talk about. This guy here in the pink is a denominator. It's always a squared. So this number is always going to be 0. Okay? Because this is squared, right? So the only way you can have a negative on this side, on the left side, would mean that c has to be less than 0. Or else you won't be able to get a negative sign, right? If you wanted to do that, so you're looking for only values of c that are going to satisfy this equation are going to be the values of c less than 0. But because our domain of analysis, if you go back a page, what you'll see is our domain of analysis is between 0 to 8. We cannot jump back. Okay, so C will belong outside the domain of analysis, which means this function does not satisfy the mean value theorem in the given domain. So the answer to this short way will just be that the C does not exist. In other words, there's no C, there is no C value in 0 to 8, so that the f prime of C will be equals to f of 8 minus f of 0 over 8 minus 0. Let me just correct that a bit. Let me rewrite that so it's not a big trouble here. To avoid confusion. So f of 8 minus f of 0, or 8 minus 0. Because we figured out C has to be negative in order to make it true, but 0 to 8 is only positive numbers up to 8. So we can conclude there's no values to satisfy the mean value theorem here. Alright, let's go ham on all these together. Question 9 is also another mean value theorem. So now what they've given you is that they told you that a derivative of a function f of x, okay, is bounded between the values 4 and 6 in my case. So the derivative value cannot exceed 4. Cannot be less than 4, it cannot exceed 6. It has to be in between those, right? And then they want you to find out this guy. So what they have is a very vague thing written out here. A dash here. They wanted to find out f of 4 minus f of minus 2 less than something. So by the looks of it, you kind of have a feeling that you're going to apply the mean value theorem because you see something on top. What you can do is, what you can conclude here is f of 4 minus f of minus 2 divided by 4 minus of minus 2 is similar to the form of f of b minus f of a over b minus a. Okay? And if this satisfies the mean value theorem, then you know this must be equals to the derivative at a value of c. So if you think about this in this sense, right? Let's go to the next page first of all. So we had f of 4 minus f of minus 2 over 4 minus of minus 2, so we get 6 at the bottom. That inequality is going to be equals to the derivative at the point C, which we don't know yet, right? But we are not worried about looking for the actual values of C, but we just want to figure out the bounds on this quantity up there. So for the max value that this can ever take, so the max value of this whole thing must be the max value of the derivative, which we got. So in this case, the max value was 6. So the max value, the f of 4 minus f of minus 2 over 6 can ever take in this situation is always has to be less than or equals to 6. Right? Hence, what you can see is you can figure out the upper bound on this. The upper bound, f of 4 minus f of minus 2, will just be less than or equals to 36. Because if you send the 6 on the right side, you multiply both the sides of the equation, put 6 to get that 36. So, okay, cool. We figured out the first upper bound. Similarly, we can find the lower bound by saying the value of this piece right here cannot go below 4, right? So if you use that thing, the minimum possible value will be f of 4 minus f of minus 2 over 6. Okay, it will always be greater than or equals to 4. So you can find a lower bound, which is the lower bound value is going to be 6 times 4, that is 24. So the number f of 4 minus f of minus 2 will always have to be greater than or equal to 24. So we figured out the bottom bound. So the answer to this whole problem will just be 24 less than or equals to f of 4 minus f of minus 2 less than or equals to 36. So the condition on the derivative that we got from the beginning right here, if you go back a page, you'll see at this condition right here limits whatever the values of this guy is going to be if you apply intermediate value theorem. Okay. All right. I think there's one more value on that, so let's kind of figure that out. Problem 10 here. Problem 10 talks about suppose that f is a differentiable function such that its derivative will always be less than or equals to 6 in my case. Okay. For all the values, for all the x that belong in -1 to 3. So if you function x value between that, you can always get this. So now if we know, they gave us a little bit of information here. So f of -1 is given out to be 3. How do we use that information? And they said using MVT, find out a bound on f of 3 is less than v. So we're looking for the v value. So now we have to frame the argument in a way that we kind of figure out the whole situation using the mean value theorem. So if you're trying to write the mean value theorem form of the secant line for the function in this domain, what you write is you'll say f of 3 minus f of -1 over 3 minus of -1 must be equals to the derivative value at some unknown c. Okay, so now given all those pieces of information that you have up there, what you can isolate is you can say f of 3 is just v, so you're going to keep that. Because we have a lower bound that it cannot exceed it, we have to use the lower bound on the actual function's derivative as well. If f of 3 cannot exceed v, then the derivative cannot exceed the value 6 as we got in this condition. So if you replace all of them, what you get is v, and we know f of -1 is 3, so minus 3 over 3 minus a -1, so you get 4, must be less than the max possible value of the derivative, which is 6. So now from here, it's very easy to isolate for v. If you do so, you get v minus 3 less than or equals to 24. And now given that information, what you can do is you can move the 3 on the right side, you get v less than or equals to 27. And now the smallest possible v you got to pick up is just 27. Okay, and that's it. That's it for the mean value theorem problems. Now we're going to start to talk about the other calculus tools we're going to need in this assignment.